Hello, everyone. I'm Andrew Boutros, and today I'll be presenting our work on the specialization of AI inference processors on FPGAs. This work was done at the University of Toronto and the Vector Institute for Artificial Intelligence in collaboration with Intel Programmable Solutions Group. There's no doubt that artificial intelligence technology is reshaping our world. Not only has it become an indispensable component in our day-to-day life, but it has also resulted in major scientific breakthroughs. For example, earlier this year, Project AlphaFold from Google used AI to solve the protein folding problem, which remained a mystery for many decades. From a string of a few dozens to several thousands of amino acids, AlphaFold uses AI to predict with very high accuracy the 3D structure that protein folds into, which helps us understand what it does and how it works. This can significantly accelerate the process of developing treatments for diseases or enzymes to break down industrial waste, for example. On the other hand, conversational AI has also witnessed great progress in the past few years with models like GPT-3. These models can understand large bodies of literature, respond to questions about them, and even summarize their core ideas. This has been recently used to create GitHub Copilot, where software developers can peer program with an AI model. And who knows, maybe in a few years from now, AI models can even understand, debug, and code computer programs on their own. However, these breakthroughs do not come for free. In the 5 years between 2015 and 2020, AI model complexity, which is reflected by their number of parameters, has drastically increased by about 3 orders of magnitude. This rate of growth in AI computational demands is much faster than what our current compute platforms can keep up with. Therefore, data centers and service providers resort to deploying custom processors to specifically accelerate AI computation. But the key challenge is that the advances in AI algorithms and changes in their memory and compute requirements are very rapid, much faster than the development, manufacturing, verification, and deployment cycle of a new computer chip. And this is exactly where I feel programmable gate arrays, or FPGAs, really shine. They consist of arrays of programmable logic and routing that can implement any digital circuit, along with hard functional units such as digital signal processing or DSP blocks, block RAMs, and even complete processor subsystems. This enables building custom hardware for accelerating AI and at the same time provides the flexibility to reconfigure it anytime after deployment as AI algorithms change. However, there are 2 key challenges that face the large-scale adoption of FPGAs for AI acceleration. The first key challenge is whether it is possible to achieve competitive AI inference performance using FPGAs despite the overhead of their reconfigurability. And the second challenge is how can we make FPGAs usable by AI application developers who come mostly from a software background with very little or no hardware design expertise. In this work, we use a design approach to address these key challenges for AI FPGA-based acceleration. This approach is what we refer to as the overlay approach. In the traditional FPGA design approach, designers start from an application that needs to be accelerated. They implemented an RTL, compile it for long hours using FPGA CAD tools to synthesize, place, and route the hardware design, and then they keep optimizing it until meeting the performance requirements. In the overlay flow, on the other hand, a group of experts start from high-level domain requirements and design a software-hardware contract that we call an instruction set architecture, or an ISA. Then they develop a software toolchain for it, such as a compiler and a simulator. After that, they develop a general overlay architecture and optimize it to obtain a high-quality bit stream. Then, any user doesn't have to know any hardware implementation details or go through long hardware compile iterations to meet performance. They just write their applications in a high-level software language, which are then compiled using the overlay compiler into instructions or binaries that can run on the custom processor deployed on the FPGA. Therefore, AI application developers or users in general can go from the applications to FPGA deployment without the need for any hardware design expertise in the overlay flow, unlike the traditional flow that involves writing RTL and very long run times of FPGA CAD tools. To illustrate the power of the overlay flow, we implement the Neural Processing Unit, or NPU overlay, which is a custom VLIW soft processor with a chain of 5 coarse-grained units. And the two key design principles of the MPU is first, to amortize control, such that a single instruction can trigger the execution of thousands of operations. And second, to exploit the FPGA flexibility to build a custom memory subsystem and make use of the tremendous on-chip VRAM bandwidth. The heart of the MPU architecture is a matrix vector multiplication unit that consists of multiple tiles, each of which has a number of dot product engines and vector or matrix register files. This is followed by units that perform vector element-wise operations used in AI models like activation functions, additions, and multiplications. And finally, there's a load store unit that communicates with the outside world via a FIFO interface and can write back the results of the pipeline to any of the architectural states or register files in the MPU architecture. One key takeaway from my brief description of the MPU architecture is that it is massively parallel. Thousands of operations are being executed by the processing pipeline every cycle. This architecture is then compiled to generate a single high-quality bit stream that is deployed on the FPGA, and then AI application developers can program it purely through software to accelerate their models. To illustrate that this approach can deliver state-of-the-art AI inference performance, we compare the MPU implemented on the new Intel AI optimized FPGA, the Stratix 10NX, to the same generation AI optimized GPUs, the NVIDIA V100 and T4. Notice that the FPGA has a smaller die size than both GPUs, especially the V100. This graph shows the normalized performance compared to the T4 GPU across a wide variety of AI benchmarks, showing that on average, the MPU overlay on the Stratix 10NX FPGA can achieve about 23 times better performance than the T4 GPU and about 11 times better performance than the much bigger V100 GPU on low batch inference tasks. And if we revisit the two key challenges for the adoption of FPGAs for AI acceleration, we can see that the MPU overlay can achieve an order of magnitude better results than equivalent GPUs due to its custom hardware architecture that better suits these workloads, and can be easily programmed by generating a single bit stream that can be programmed to run many different workloads purely through software. However, our benchmark suite contains a wide variety of workloads such as simple matrix vector multiplications, fully connected multi-layer perceptrons that are commonly used in recommender systems, as well as things like recurrent neural networks, gated recurrent units, and long short-term memories that are commonly used for natural language processing. This means that the MPU is general, which is good from a productivity standpoint, as a single bit stream can be programmed to run all these different types of models through software. But what are the performance and area costs that we pay for this generality? And can we further exploit the FPGA reconfigurability by specializing the MPU architecture only for a specific workload or a group of workloads that we are interested in? By looking at the MPU processor architecture and analyzing the different workloads it supports, we can see that in many workloads, a lot of the compute units in the MPU pipeline are left unused, and those are the ones colored in gray in this figure. Therefore, we can actually start to specialize the MPU for each class of workloads to achieve higher efficiency. And this can be done in three different ways. The first is eliminating the compute units that are not needed for this class of workloads. The second is reordering vector element-wise operations in the MPU pipeline, and also reducing the capacity of register files to exactly match the needs of this workload. To explore the MPU specialization design space, we developed a System C architecture simulator that allows us to rapidly model and evaluate different variants of the MPU architecture. As an example for what we can model using the simulator, this figure shows the MPU variant specialized to run only multi-layer perceptron models. And this one is another that can run gated recurrent units and long short-term memories. This graph shows the performance results of the baseline MPU architecture obtained both from RTL simulation, which is cycle accurate, and our System C simulator for all different workloads. It shows that we can estimate the MPU performance using the System C simulator with only around 5% average error, but 26 times faster than RTL simulation. Therefore, it enables highly accurate and rapid design space exploration. For our MPU specialization study, we first explored the design space using the System C simulator to obtain the best MPU architecture for each individual workload. Then we modified the MPU RTL to implement different variants and compile a new bit stream for each workload. This allows us to obtain the resource utilization results and bitstream compile times for the specialized NPUs. This graph shows the performance and area results of the specialized NPU variants compared to the baseline NPU shown as the dashed black line. It shows that specialization increases performance as all the red bars are higher than the dashed line, and at the same time it saves area as all the green bars are below the dashed line. By looking at the average gains for different classes of workloads, we can see that the NPU specialization can result in up to 35% better performance and 44% area savings. And from the designer productivity point of view, it takes about 230 to 340 minutes to compile a new bit stream for each new workload. However, once a workload is compiled, it can then be added to a library and used to reconfigure the FPGA whenever this workload is required to be run. To summarize, the reconfigurability of FPGAs is very valuable for AI acceleration in data centers due to the rapid advances in AI models and the changes in their compute and memory requirements. However, there are two key challenges for the adoption of FPGAs for AI acceleration, which are the overhead of reconfigurability and ease of programming. The NPU shows that the overlay design approach can address these challenges as it can achieve an order of magnitude higher performance than equivalent GPUs, and at the same time can be purely programmed through software. Furthermore, we can exploit the FPGA reconfigurability by specializing the NPU for a specific workload or group of workloads to achieve up to 35% higher performance and 44% lower resource utilization. And this comes at the cost of about 4 to 6 hours of bitstream compile time for each new workload. However, once a workload bitstream is compiled, it can be added to a library and reused later. Thanks for your attention. I'll be happy to take any questions during the discussion session after the talk or via email. Thank you.